Okay, welcome to lesson 1.5 on investigating transformations of functions. And in this lesson, we're going to actually start to talk about the general form of a transformed function. So we've looked at the four base functions that we have, but we're going to look at what it looks like in this form for learning target 5. And we're going to start to look at learning target 6. This is going to come up more in the next couple lessons, but I want to put that down. It's just talking about horizontal stretches, compressions, determined by the reciprocal of the coefficient, and coefficient needs to be factored out. So this needs to be factored out thing, we're going to look at that not in this lesson, but in the next lesson, and then I can explain using an example why it's the case. And we'll talk about, we'll show an example of how that is in the coming days. First off, we just look at the base function absolute value of x. And we're going to actually just use function notation. And this came up in the second lesson, the homework, just actually simplifying this. Okay? And so this is a warm-up question. You can try it on your own and then just kind of pause it. And I'll just keep going through the lesson. So what we have to do is replace x with x minus 3. And so for the first one, we actually just have equals absolute value of x minus 3. So that's what it looks like in the actual function. The second one is we're just multiplying the function by 2, so we get 2 absolute value of x. The third one, we're adding 3 to the function, so it looks like this. And the last one, we're subbing in 3x, not x. And so we've got the absolute value of 3x. Okay. The reason why we walked through that for that one is because, like, in our investigation today, where students would use like the computers, this is the first step, is to actually know what to sub in. And so what we're saying here is x minus 3, and we can actually use different functions for that transformation, the x minus 3. Okay. And so here's the instructions. First thing we're going to do is graph the base function using Desmos, and I'll show you how to do the first one. And then we're going to graph each of the transformed functions, and then we're going to write down the equation of the transformed functions and observe the relationship. So you'll write down the equation like we did in the warm-up, and then in the end, so you don't have to write anything like any of the observations down, you'll make it at the end. And so to walk through these, so we're going to start off with the f of x plus c transformation. And so we start off with the base graphs. We go to Desmos. Desmos is really quick to get to at any time. And so if we start off with the base graph, f of x equals the x squared graph. I'm just going to put it in projector mode so you can see it a little bit better. What we want to do is take x squared and add 5. And so for each one of them, we're going to add 5 to it. But we're going to see what happens when we take x squared and add 5. So we just make a new function. We'll call it g of x, or we can call it y, equals f of x plus 5. So it looks like this. Okay. And notice how that's the same thing as x squared plus 5. Okay. And so what's happened is, like, it's actually maintained its same shape, but it's been shifted up 5. Okay. We can see the same result if we change this to the square root of x. So we take this guy, square root of x, and we can see that the original graph is the red one, and then this is the up 5. We do the same thing with the minus 6 as well, and so we just write down all the equations, so we can see what 1 over x looks like. And we can actually make this guy f of x plus 5, and so that when we change this guy to the absolute value, you can see the effect. Okay. And then if we change that to a minus 6, you can see what happens after that. So you can see, and then if we change this to the square root of x, that's kind of neat. The blue graph is f of x minus 6. Okay. And then we can actually, what we could do is we could just say plus d, and then add a slider. And so we can actually slide d to different values. This is something that Desmos does, and you can see the shape actually doesn't change. It's the identical shape to the base graph. It's just shifting it up or down, depending. And so when we talk about this one, when we're describing the effects, we just say it vertically shifts the base function up if positive, down if negative. Okay. This one's similar. And so we first off we draw what we write down the equations, and then we can write down the equation of both. And what we actually see is like an opposite effect. So if I like put the plus c in here, sorry, if I do minus 4, that actually shifts it to the right 4, which you guys saw in grade 10, and plus 4 actually shifts it to the left, almost opposite of logic. So you say like minus c and add a slider, and then positive values, so subtracting like 5 and then subtracting a negative would move it left, so without adding. Okay, and if we change this to 1 over x, we get the same kind of thing. It's shifting left and right. Okay, and so what we do is we say that's actually seems horizontal shift to the base function. It appears opposite of logic. The minus 4 shifts to the right, and the plus 2 to the left. That almost seems like opposite of what we would think was happening. But this is the key sentence here. Since we're subtracting 4 to the inputs, we need larger inputs to get the same output as the base function. So we add 4. Okay? And so what happens is, like, if we look at the values here for the base function, let's just look at a simpler one, the absolute value function. If we're going to take this function and subtract 2 to the inputs, so the red guy, so this red guy is the base function, and this is if we subtract 2 to all the inputs. What happens is you need actually bigger inputs. So notice that, like, 0, so negative 2 no longer gives 0, or sorry, 2, it gives, negative 2 gives 4. It's 0 that gives 2, and then it's 3 and then 4, and so we actually need bigger values to get the same original y values, which is 2, 1, 0, 1, 2. Because all of these x values, we're taking away 2 from them, and so we actually need to start off with bigger numbers like 0, 1, 2, 3, 4 to get to the same values. Like these y values weren't actually in the original point, and so we can we can delete them out. But we actually need bigger values for x because we're subtracting 4 from them to get to the same value for y, and so we need to add 4 to them. Okay. The next one, what we see is a multiplier on the outside of the function, and so what that looks like is if we look at the base graph f of x, and we say that y equals f of x times 2. You see what happens, like we can convert both of these to a table. All the x values stay the same, but all the y values, they just double. And so like this height doubled, this height doubled, this height doubled. And so if we did something like a half, 1 over 2, all the y values now half. So this guy was 2, now it's 1. 1 becomes a half, so all the y values a half. And then if we did something like minus 3, all the y values triple, so it's so these y values that were 21012 become 63036, but they also become negative. And so even though it's an absolute value function, the negative is on the outside. It shows up like this here, -3 absolute value of x. But it now it's opening down, much like a parabola. If you remember parabola opening down, if the a value is negative. Okay. And so if you look at all of the different notations, this one's a little bit trickier, like the 2 bracket 1 over x. You often see the 2 up here. It looks different depending on which function it is. And then if you have a half 1 over x, you could see the 2 in the bottom. But notice that it's always, we can really actually call this one a horizontal as well. It does the same effect. But you can also see it on the outside. And then we can actually bring it in. Math tells us we can multiply the tops and multiply the bottoms. So the -3 can go up top, or the negative can stay on the left and the 3 can go up top. Or we can just write -3 on the outside, 1 over x on the inside. And so in summary, what happens is we get a vertical stretch or compression. Stretch would make it bigger, compression makes it smaller. If it's greater than 1, you get a stretch. If it's less than 1, you get compression. And if it's negative, it's a vertical reflection, so it opens down. We also call this a reflection on the x-axis, and that's because, like you saw, this is the x-axis. It's vertically reflecting down. Okay. The next one, we're multiplying the inputs by 2. So it looks something like that. Notice how this one looks very similar to that vertical compression. And the last one, or the next one, we're multiplying the inputs by half. So notice how here we put a half x, or you can write 0.5x, just a little bit nicer, so you don't have a fraction over a fraction. 1/2 x. And then the inputs by a third. Okay, so again, you could write like 0.3333x instead of writing a fraction. Okay, and so we see what that does. If we take the base function and multiply the inputs by 2, what happens is to get to the same values for y that we had originally, you only need half the size. Because we're multiplying the inputs by 2, to get to these same 21012, we could do that with -1, -1/2, 0, 1/2, and 2. So we need half. Like you can see, 1. So like these are the outputs 21012 for the original function. To make those the same, so to get to the same outputs, I'll just delete this guy. I don't know if I can delete that. Yeah, so to get to the same outputs, what we do is we half the input. So we take half the size. And so what we call that is, because we're multiplying the inputs by 2, we call that a horizontal compression, because we half the inputs to get to the same output. And you can see that here, like where this is the original function, this is the transformed function, and it's half the size horizontally. We call it a horizontal compression. If we took the inputs and multiplied them by half first, notice that we actually need double the size now of the input to get the same output. and 4. And so to get the 2, 1, 0, 1, 2, you actually need to double the inputs. And so since you have to double the inputs, because we're halving the inputs, you actually need to think about what double the inputs are, and then because they're going to be halved after, to get to the same output, same height. And so you can see that here. With this is the base function, the smaller one, and the horizontally stretched one by a half. And then negative 1/3, what it does is here it actually doesn't do anything because it's a reflection in the y-axis, and that doesn't change anything. Absolute value is still the absolute value, so it doesn't change anything. But if we had something like the root x graph here, when we do a negative sign, so I'll just change this back to x, so you can see, when we do a negative sign, it actually becomes a horizontal reflection. Okay? And so just to summarize, we're just looking at the horizontals. They actually seem opposite of logic. Just like the horizontal shifts were opposite of logic, these ones are too. And so horizontal stretch, compression, reflection, it appears opposite of logic. Less than 1 is actually a stretch, like a half is a stretch, because we're halving the inputs. We need double the size to begin with. Greater than 1 is a compression, and so 2 is actually a compression because we're doubling the inputs, so we need half the size to begin with. And it's the same reason as a shift. And then this guy will be the horizontal reflection. Okay? In summary, we actually have all these letters in different spots, and they do have to be in these forms, like this k has to be factored out. A gives you a vertical stretch compression, negative gives reflection. I would say that's not opposite of logic, that's with logic. Like a 2 is a stretch, that makes sense. K gives a horizontal stretch or compression, so it's almost opposite of logic, like a bigger number is a compression, makes things smaller. And a negative gives a reflection. The D is horizontal shift left or right, almost opposite of logic. We note that we do need factored form, otherwise things do get messed up here. So this does have to be in factored form inside the function. So this would be like a square root here, or a 1 over x, and this all stuff would be in the denominator. It all looks different depending on which graph you're looking at. We'll see different ones. And C is the vertical shift up or down. Vertical is always on the outside of the function, so notice that with the different ones, like this, the a value here was on the outside of the function, so it was after you square rooted it, you multiplied by 2 after you squared it. The d is on the inside, the c, the vertical guy, is on the outside, so after you square it or square root it, you're adding 5, or after you do the reciprocal, you add 5. That's what I mean by the outside of the function. Okay, horizontal are on the inside, verticals are on the outside. Horizontal are opposite of logic, and vertical are with logic. Okay, and usually what happens is, like when we're graphing these, we'll see we're going to do the stretches, compressions, reflections first, just because those change the shape, and these will shift the points after. Okay, so for homework, we're going to work on the transformation package that's shared in this folder, handed out in class, and we're going to have a quiz tomorrow on the first 4 learning targets, so not including this one. Okay.